Hi again. As I mentioned in the previous video, here we want to understand the discrete, the residue class field and map for the places P infinity. And for this purpose, let me briefly recall the definition of the valuation ring O infinity that contains the fractions whose degree of the denominator is less than or equal to the degree of the denominator. And we say that it's a unit if they have the same polynomial degree, and P infinity will be the maximal ideal, and it will be generated by X inverse, the transcendental X here, or in other words, X inverse is a prime element for P infinity. And when we consider the discrete valuation map, so here it will be denoted by, let me use the notation for P infinity for the place P infinity. And in general, we know that given a place, we can define the discrete valuation map depending on their presentation, in particular depending on the powers of the prime element in their representation. So by the definition, we can easily see that the valuation V infinity of X inverse is 1. And now we want to first show that valuation of any rational function field is determined by the difference of degree g of x and the degree f of x. And in order to see that, we just try to apply the definition of a discrete valuation map, which is obtained from the given P. And here our purpose is to write f over g in terms of the prime element times a unit from O infinity. So that means these two polynomials should have the same degree, must have the same degree, and this forces n is degree g minus degree f. And this allows us to write f over g in terms of the prime element n and the fraction from O infinity. And now our second claim, the corresponding residue class field, in this case isomorphic to K. And as we have seen in the previous example, in order to see this isomorphism, in the discussion session, we will talk about how we can define K-linear map from the polynomial ring with variable X inverse to the residue class field F infinity. And then we will conclude that this is also onto map, and by applying the first isomorphism theorem, we will see that the residue class field F infinity is isomorphic to K. And now residue class field residue class map. Now indeed we want to understand how the residue class map look like. So that means we want to understand the images of Z when Z O infinity And by the definition, we have if z not O infinity, we have B set infinity. And in order to see that explicitly what kind of evaluation of set at P infinity we have, let me explicitly write a function z as f over g in terms of degree n and degree n polynomials. And let me also define z of infinity if n is less than or equal to, strictly less than or equal to 0, B set infinity for the same degrees. We consider the fraction of the leading coefficients of f and g. And when n is strictly bigger than m, we will set infinity. And now our claim is that indeed this map or its sorry, its image zp infinity is determined by z infinity we defined here. So to see this equality, let me consider the two cases. If z not O infinity, by the definition of the O infinity, it means that f over g is not an O infinity, so that means degree f is strictly bigger than degree of g. That means n is bigger than m. And by the definition of z infinity, in this case, we have infinity. And by the definition of the residue class map, we also have z of p infinity is infinity, and we get the equality. And now we want to see that in this case, z of p infinity also determined by these two cases. In other words, when we consider a function z in O infinity, and similarly, if we write it as fractions of f and g, or more explicitly, polynomials of degree n and m. Here first, let me take x to the m and x to the m parentheses. Because here, in some sense, we want to get terms which belongs to p infinity. And here you call that p infinity is generated by the x inverse. And similarly, when we take the parenthesis x to the m parenthesis for the denominator, sorry. We also see that these terms belongs to p infinity. But here n and m, bm are constants. And when n is equal to m, we get, or more explicitly, when we consider the evaluation of z at p infinity, and if n is equal to m, we obtain nm over bm. And this is also by the definition of Z infinity the same constant. And if n is equal to m, in this case, this term can be written as 1 over x to the m minus m. Here, m minus m is strictly positive. So that means it contains x inverse in the refactorization. That means whole set lies in P infinity. So that means this is P infinity. That means this is the zero of the residue class field. And this is also consistent with the definition of Z of infinity. And for the rational function fields, so far we have considered two types of places. One is determined by the irreducible polynomial P of x, and the other one is P infinity, which is generated by the x inverse. And in the next lecture, I'm sorry, we will also consider the residue class field and maps. So now our next question is that do we have any other places which are different than these two of them in a rational function field? And in the next lecture, we will investigate an answer, and we will see that these are the only places in the rational function field Q of x. So for the moment, this is all what I want to say. Thank you for your attention. Stay in health and see you next week. Bye-bye.